these squiggly lines here, they're not exactly squiggly, they're kind of pointy. Anyhow, these symbols represent resistances. Okay, so let's say this represents resistance R1, perhaps the resistance through a bulb. There are other circuit elements that have resistances, but let's say that this represents the resistance through a bulb, and this the resistance through another bulb. And we have a current I flowing through these two resistances, okay, flowing through the circuit. And since current can't, or since charges can't build up at a point in this circuit, the current flowing through one must be equal to the current flowing through the other. The current that gets through here has to go someplace. The only place it has to go is through here. It can't sit around and accumulate. In that case, we have a voltage V1 required to drive the current across this resistor, and a voltage V2 that's required to drive the current across this resistor. And V1, the voltage that we need to attain the current I across resistance R1, is just I times R1. Recalling that R is just V over I. That's the definition of R. We have the voltage is just current times the resistance. And here we have the voltage V2 is current times resistance R2. It follows that the total voltage from here to here is just V1 plus V2. Now, we'll go back, we'll continue with the algebra in a second, but the voltage is the sum of these two voltages, and let's see what that means. The voltage is indicated by the rate at which you have to crank the generator. That means that if we wanted to get this current just through this resistor, we would have to crank the generator at the rate that gives us this voltage. Let's just say that we had to crank it at 1 cycle per second, or 1 revolution per second. If we then put the generator across this resistance and got the same current, we'd need the voltage IR2. And let's say that corresponds to having to crank twice a second. Now, if we have to crank once a second to get this and twice a second to get this, we have to crank 3 times a second to get the whole thing. That is, the voltage across here and the voltage across here add up. We have to supply enough voltage to get the current through this as well as through this. We have to crank harder. Okay, so the voltage is the sum of the two voltages, V1 plus V2. And we can see clearly, since V1 is IR1 and V2 is IR2, that that's I times a quantity R1 plus R2. And if we say that that's I times some equivalent resistance, R, then this equivalent resistance has to be R1 plus R2. So if we have voltage equals current times total resistance, that is, we ignore the fact that we've got two circuit elements here. We put a black box around this thing and crank it and measure the current and measure the voltage. We're going to see that the current and the voltage are related by the resistance that's equal to the sum of these two resistances. And that just follows from this argument here. If, on the other hand, we have a parallel combination. Now, you've seen the parallel combination in the experiments. I haven't demonstrated one in front of the camera here, but that is demonstrated on the experiment videos. We see that we've got the source here someplace, and we provide alternative paths. The current can flow through the resistance R1, or can branch off and flow through resistance R2 before it comes back and recombines. And you should relate this to where the clips go when you set up this circuit with the two bulbs. Okay, the current I1 that flows through here, the current I2 that flows through here have to obey the same relationship. The voltage from here to here, the voltage here is the same as it is at this terminal of the generator. The voltage here is the same as at this terminal. This is because voltage doesn't change through the wires. Now, I don't know if I've mentioned that as clearly as I should have. The voltage in one part of a wire, unless it's a real thin wire, something with a lot of resistance, is the same as at any other part of the wire, because if there's no resistance in the wire, then a current flowing through the wire won't be associated with any voltage. Okay, if the resistance was 0, then you wouldn't need any voltage at all to get as much current as you like. Now, that's not really precisely the case here, but there is a little bit of resistance in any wire. But usually you get a big enough and thick enough wire that its resistance is so small that you can completely ignore it. And you can make the approximation, a very good approximation, that the voltage at every part of that wire until it goes through resistance has to be the same. So the voltage everywhere from here to here, this point, this point, this point, this point, and this point, is the same as it is at this terminal of the generator. The voltage at all these points on the other side of the resistors is the same as at this terminal of the generator. Now, it follows that I1 times R1, which is the voltage difference between here and here, has to equal V. So that I1 is just this voltage between here and here divided by R1. I2 is just the voltage between here and here, which is again V, divided by R2. The equivalent resistance is going to be V over the total current. Now, what's the total current? Well, it's just I1 plus I2. And when we add the currents up down here, we see that the resistance is V over I1 plus I2. Substituting V over R1 and V over R2 for I1 and I2, we get this equation. We can divide by the voltage and we get this. And rearranging the equation here, I confused myself for a minute. I thought I'd already said this, which made me think that I'd said the wrong thing for the series circuit, but that's not the case. A couple of minutes ago I typed something into the page, but that's what confused me, so forgive the pause there. Anyhow, the 1 over R will therefore be 1 over R1 plus 1 over R2, and R is going to be R1 times R2 over R1 plus R2. Okay? Now that is, resistance is 1 over this, so that this is the reciprocal of the resistance. We get this equation, which we easily solve for R to get this. Both of these are very important. This is what goes on. This is what's illustrated by the parallel circuit. And this is the algebraic rearrangement that allows you to compute the equivalent